Long ago, our solar system did not exist. There was only a vast, cold cloud of gas and dust, a nebula. It drifted for eons, then began to spin. Gravity pulled matter inward, igniting a growing core. A star was born, our sun. Around it, a flat, spinning disk of gas and dust took shape. Tiny grains collided and stuck, like snowflakes forming a snowball. Pebbles grew into rocks, then boulders, and finally, planetesimals. The young system was crowded and violent, constant crashes, shattering and merging worlds. Orbits shifted with every close pass and gravitational tug. Forming giants plowed through the disk, carving paths and stirring debris. In this turbulence, the fate of every world, Neptune included, was decided. Gravity is the architect of the cosmos, the force binding all matter. It keeps the moon circling Earth and planets orbiting the sun. Close passes exchange energy and momentum, forever changing orbits. This slow reshaping is planetary migration. Worlds can spiral inward or drift outward over millions of years. Interactions with countless planetesimals act like tiny, cumulative pushes. Throw debris inward and the planet is nudged outward, energy conserved. Over vast time, tiny nudges move giants great distances. The giants likely formed closer together, then drifted. Saturn, Uranus, and Neptune outward. Jupiter briefly inward, then out. Migration reshuffled the planets and sculpted belts, comets, and asteroids. The final arrangement, and Neptune's distant seat, was not guaranteed, but earned through gravity's long work. For decades, many thought planets formed where we see them now. New evidence challenged that simplicity. The NICE model offered a new, dynamic history. It begins with the giants packed between 5 and 15 AU. A key trigger, Jupiter and Saturn crossing a strong resonance. The ice giants then plowed through a massive, icy planetesimal disk. The chaos settled into the architecture we see now. Named for Nice, France, where the model was developed in 2005. It unified migration, resonances, and a late instability into one coherent story. And in that story, Neptune's path may have skirted the edge of exile. Orbital resonance occurs when periods align in small ratios, like 2.1 or 3.2. Resonances can protect orbits. Pluto and Neptune never collide, but they can also amplify small tugs into chaos. As Jupiter and Saturn drifted into a 2.1 resonance, their pulls strengthened. Disturbances spread outward, destabilizing the ice giants. The system entered gravitational instability. Order broke down. Close encounters can fling giants onto new trajectories. In such turmoil, even ejection from the solar system becomes possible. Uranus and Neptune scattered the icy disk like bowling balls through pins. We test these ideas with powerful computer simulations. Thousands of runs explore many possible beginnings. They reveal which outcomes are plausible and how often. Some runs are violent. Close giant passes become extreme. In a significant fraction, one ice giant is ejected entirely. 5 giant scenarios often lose the extra planet, leaving 4 like ours. In successful cases, Neptune can be scattered onto a long, distant ellipse near the edge of escape. Interactions with the icy disk then slowly circularize its orbit, pulling it back from the brink. A narrow escape, gravity, debris, and chance restore stability. Our picture has evolved dramatically. First, we learned planets move with mathematical grace. Then, computers showed long-term chaos in planetary motion. The discovery of the Kuiper belt revealed a vast debris field. Many objects locked in resonance point to Neptune's outward sweep. In 2005, the NICE model unified migration, resonance, and instability. It explained Jupiter's Trojans, the late heavy bombardment, and Kuiper belt structure. Later work refined physics and explored broader starting conditions. Variants include a 5th giant and timing shifts for the instability. Each study adds a layer. The reconstruction grows more precise. From Pluto's discovery to rogue planets, milestones chart a dynamic solar past. If systems eject planets, the galaxy should teem with rogues. Rogue planets are free-floating worlds, unbound to any star. We find them with microlensing, Gravity briefly magnifies a background star. A short, telltale brightening betrays an unseen planet. By watching millions of stars, we catch these fleeting signals. Several rogues have been found, evidence that ejection is real. There may be billions in the Milky Way, perhaps more than stars. The Roman Space Telescope will run massive microlensing surveys to find many more. Exoplanet systems, with hot Jupiters, tilted and eccentric orbits, show migration and scattering are common. Neptune's journey highlights a delicate balance of forces. Gravity creates stars and planets, and can cast them out. Today, our system enjoys long-term dynamic stability, a pattern that emerged only after profound upheaval. That stability let Earth keep liquid water and a life-friendly climate. A lost giant could have shifted Earth's orbit, ending habitability. Our stable outcome was one of many possible draws. Neptune may have neared the edge, then settled into place. From chaos arose order, and with it the fragile conditions that make our world possible.